Welcome to today's Explainer. We're diving straight into the mechanics of building a multi-class classification model using PyTorch. If you've ever wondered how a neural network chooses not just between two options, but among several, well, you are exactly in the right place. Today, we're taking a massive step up from simple yes or no binary predictions to a full-blown multi-class system.
Here's our quick roadmap for today. Data prep and setup, converting our data to tensors, building the actual model, running the training loop, evaluating and predicting, and finally, your turn to practice.
Section 1. Data prep and setup. All right, let's jump right into the setup. We can compress our data prep into 3 rapid-fire steps. First up, we load the famous iris dataset. Fun little fact about this one, it was actually introduced by statistician Ronald Fisher way back in 1936, and it is still the gold standard for testing algorithms today. Every single flower in this dataset comes with 4 distinct numerical features: sepal length, sepal width, petal length, and petal width. Our ultimate target? To predict the specific species of that flower based on those numbers. Second, we perform a standard 80-20 train test split, so we have a solid chunk of completely unseen data to test our model on later. And third, we scale those features using scikit-learn's standard scaler. That scaling step is absolutely crucial, because keeping our data features on a similar numerical scale ensures our PyTorch optimizer can run smoothly and efficiently.
Moving on to Section 2, converting data to tensors.
Now, there is a really critical contrast you need to watch out for when converting your pandas data frames to tensors in your code. Your input features, those petal and sepal measurements, require the standard torch.float32 data type. But your multi-class target labels? They specifically require the torch.long data type. Why the difference? Well, it's because multi-class labels aren't decimal measurements at all, they're integer class IDs. In our case, it's 0 for setosa, 1 for versicolor, and 2 for virginica. PyTorch's multi-class loss function is hardwired to expect those exact integer IDs to calculate the loss correctly. Section 3. Building the multi-class model. Building the architecture itself is actually beautifully straightforward. Our nn.linear layer takes an input size of 4, perfectly matching those 4 flower measurements. But here is the major shift from binary classification. Our output size is 3. Because we are choosing between 3 distinct flower species, our model has to output 3 raw scores, which we call logits, for every single flower we feed into it. It doesn't just spit out one single number anymore. It gives us a dedicated, separate score for setosa, 1 for versicolor, and 1 for virginica.
But wait, this brings up a massive question. If we're suddenly outputting 3 distinct raw scores per flower, how does our model actually know how wrong it is? We absolutely cannot use the binary loss function we might have relied on in the past, right? Because that expects exactly one output score, deciding between 2 options.
To solve this, we bring in cross-entropy loss. Think of this function like an automatic gear shift that handles multiple categories perfectly. When our model spits out those 3 raw logits, cross-entropy loss grabs them and internally applies a mathematical function called softmax. Softmax looks at all 3 scores and smoothly converts them into 3 probabilities that add up perfectly to 100%. It then compares those probabilities directly to our true integer class ID to figure out exactly how far off the model's prediction was.
This perfectly illustrates the big structural difference you've got to remember when writing your PyTorch code. Binary classification uses BCE with logits loss. That expects one total score and uses an internal sigmoid function to get a probability between 0 and 1. Multi-class classification, however, relies entirely on cross-entropy loss. It expects one score per class and applies softmax internally across those multiple outputs. And here is a crucial piece of practical coding advice for you. Because these loss functions apply sigmoid or softmax internally, you should never manually apply them to your network's output before calculating your loss. Just let PyTorch handle the complex math under the hood.
Section 4. The 20,000 epoch training loop. Let's pop the hood and see how this builds our actual training cycle. We're using stochastic gradient descent, or SGD, with the learning rate of 0.01, and we are going to let this run for 20,000 epochs. In every single epoch, our optimizer repeats these 5 manual steps in the code. First, we pass our training features into the model to calculate the logits. That's the forward pass. Second, we pass those logits and the true labels directly into our cross-entropy loss function. Third, we clear out the old gradients by explicitly calling the 0_grad function so we don't accidentally mix old math with new math. Fourth, we trigger the backward pass to calculate our new gradients. And finally, we call step on our optimizer to actually update the model's weights. Over 20,000 epochs, this steady, repetitive process acts like a precision tool, driving our multiclass loss way down from around 0.60 all the way to roughly 0.08.
Section 5. Evaluating and predicting.
So here's the crucial point. When we hit evaluate on our test set, data the model has literally never seen before, our model achieves a fantastic 93.3% accuracy. It's highly capable of identifying a flower species based purely on those 4 numerical measurements.
Now, if we break that accuracy down into a confusion matrix, we get a crystal clear picture of what the model is actually doing. Looking at the matrix, we see absolutely perfect predictions for a setosa, 10 out of 10 correct. Where the model drops that roughly 6.6% accuracy is just a tiny bit of expected overlap between versicolor and virginica. It predicted versicolor correctly 9 times, but confused it for virginica once, and vice versa. The cool thing is, in the real world, versicolor and virginica have incredibly similar petal measurements, so this slight confusion is exactly what we'd expect to see from a model learning from real biology.
Now, what if we want to predict a single new flower species that we just found out in the wild? We use a specific 4-step inference process in our code. First, we pass the new scaled measurements through the model to get our 3 raw logits. Second, because we're no longer calculating loss and PyTorch isn't doing it for us, we manually apply torch.softmax across the outputs to convert those raw scores into readable probabilities. Third, we use a super handy PyTorch function called torch.argmax. Argmax literally just looks at our 3 probabilities and picks the index of the highest one. If the highest probability is the very first score, argmax returns 0. If it's the second, it returns 1. And that gives us our 4th step, the winning class ID, which maps perfectly to our target species.
Section 6. Your turn to practice.
You've seen exactly how the PyTorch multiclass pipeline operates under the hood, and now it's time for you to take the wheel. Your challenge today is to build a classifier for this support ticket dataset. Instead of flower measurements, you've got text-based features, message length, binary flags for payment, error or login keywords, and the number of previous tickets. Your target is to map these tickets correctly to 3 different departments: billing, which is class 0, technical, class 1, or account, class 2.
Armed with NN linear, cross-entropy loss, and torch.argmax, do you have what it takes to define the right input and output sizes, run the training loop, and train a model that routes these tickets perfectly on your own? The mechanics are exactly the same as our iris model. It's just a new set of data. Dive in, build those tensors, and test your evaluation accuracy. Think about it. If you can master routing these 3 departments today, what's stopping you from building a neural network that categorizes thousands of distinct objects tomorrow? The mathematical architecture is exactly the same. The only limit is your data. Thanks for joining me on today's Explainer.